So, ladies and gentlemen, last week I was talking about non-covalent interactions, and I was presenting hydrophobic interaction, and I promised you to do some explanation, and this explanation is here. So let's start with a reaction which has little to do with hydrophobic interaction, except that there is water, and the reaction is like normal water, H2O, with a heavy water, deuterium oxide, D2O. And if you mix a heavy water and normal water, and you leave it for some period of time to make equilibration possible, to get the mixture to the equilibrium, the mixture should contain certain amount of normal water, certain amount of heavy water, and certain amount of like a mixed heavy and normal water, so HOD or HDO, what you prefer. And as far as I know, it should be like if you mix normal water and heavy water in 1-to-1 ratio, you should get something like 1-to-1-to-1 ratio, so 1/3 will be normal water, 1/3 will be heavy water, and 1/3 will be this mixed water. And from the point of view of enthalpy, which is mostly driven by energy of different bonds, so the bond between hydrogen and oxygen and the bond between deuterium and oxygen is, it's not exactly, but we can assume that it's exactly. We can neglect some tiny differences. So this strength of this bond, energy of this bond is the same. So from the point of view of enthalpy, this reaction has like zero enthalpy, and there is no like driving force. If you, for example, burn coal, like you do reaction of carbon with oxygen to make carbon dioxide, there is a lot of heat released in this reaction, so the driving force which causes that the reaction goes in the way from carbon and oxygen to carbon dioxide and not in the opposite way, this is caused by the energy which is released in this reaction. But here there is no energy released, like this change in heat or heat generated by this reaction is zero. So what is the driving force? The driving force is entropy, because if you imagine you have just two molecules of water, one normal water and one heavy water, and you mix them in some micro chamber where you have just these two molecules. These two molecules can exist either in like the original form or like or in this form. So you got 50% probability of having like normal water and heavy water, and 50% probability of having this mixed water. And if you have more and more water and heavy water molecules, like millions, billions, trillions, then you can like calculate like all possible combinations, having like how you can combine oxygen with hydrogen or with deuterium, and vast majority of this combination will be exactly in this ratio, that you would get the same concentration of, if you start from the same concentration of water and heavy water, you should obtain same concentration of water, same concentration of heavy water, and same concentration of this mixed water. So the driving force of this reaction is simply like statistics, like combinatorics, that there is very little probability that if you mix water and heavy water and you leave them to intercombine, you end up with just pure water and pure heavy water and no such species. But it's much more probable that you got like this equilibrium mixture with the composition I explained. And so this is entropy. Entropy is about probability. If there is some reaction which is not driven or not predominantly driven by some release of heat by enthalpy, it could be driven by entropy. And this is also example of hydrophobic interactions. They are driven by entropy. There is very little contribution of some formation and breakage of some non-covalent interactions. They do not influence the process, but the major driving force in hydrophobic interactions is entropy. And let's start with hydrophobic interactions. So imagine that you have two molecules, one which is hydrophilic and one which is hydrophobic. So here is one hydrophilic and one hydrophobic. The hydrophilic molecule can be some molecule with some, for example, hydroxyl groups or with some charged groups. If we look at some organic molecule, it could be, for example, a carbohydrate, which are typically highly hydrophilic because having multiple hydroxyl groups. And hydrophobic molecule could be, for example, triacylglycerol, so molecule with just some CH, CH2, CH3, and few other moieties, and no hydroxyl or very few hydroxyl groups, very few carboxyl or no charged groups. So for example, triacylglycerol. And now when we put them into water, this hydrophilic molecule interacts by non-covalent interactions, by some hydrogen bonds or some similar interactions with water. And the hydrophobic molecule does not. There are no, or there always there are some interactions, but they are not so strong as in the case of hydrophilic molecule. So instead of making some bond between the molecule and the water or water atoms, this water makes some kind of shell around the molecule. And now we can look at this molecule in water with this shell of water molecules around, which form some hydrogen bonds, but they make some kind of network of hydrogen bonds but do not interact strongly with the molecule. And we can imagine that we just simply remove the molecule. So what happens? Nothing important, because there were no strong interactions between water and the molecule. So you should obtain some like cavity or some hollow space, and it's important that on this on the surface of this hollow space there are this water there is this network of water molecules which like interact with each other, but they do not point any interaction points into this space. And of course it's not very or it could be from energy point of view quite problematic to have some hollow space in the molecule. So in the next step we can imagine that we somehow keep this water network, that this water interacts with each other, but they do not point any interacting groups like this way, and there is no hollow space. So like the change in energy of this step should be 0 because there were no strong interactions, and the energy of this step should be also 0 because we didn't break or didn't form any interactions. And You can imagine that if you look, because water is quite dynamic, liquid water, these water molecules are highly dynamic, and they break and form hydrogen bonds. They are not static, and you can imagine that you can, for example, watch some water, and you can count how often you observe such a patch of waters, such a strange patch where it's not like that there are interactions here, but there is such a patch of water molecules which do not interact. And if you look at some like a liquid water, and you would look at atoms in a real time, and you would watch how this structure of water is changing, in principle you can occasionally, time to time, see such a strange structure, but the probability that you see it is very low. So, and now we come back to the entropy. So entropy is about probability. So if the probability of this strange structure of water, because its probability is low, this is unfavorable from the point of view of entropy. Its entropy is high, and therefore if you take such a non-polar molecule and put it into water, and there is another molecule, non-polar molecule, they, from the point of view of probability, they prefer to like stick on each other, because they would form such a water structure which where water interacts with each other, but they do not interact with this solute, and they prefer to stick to each other because they will reduce the surface of such a strange water arrangement. And if you, for example, put an oil into water, then these oil molecules, if you achieve to somehow disturb this emulsion to really single molecules, so after some time these lipid molecules would combine with each other, and after like some period of time you would get like two layers, one layer of water and one layer of oil, and that's why the oil is not mixable with water, because these oil particles, oil molecules, these hydrophobic molecules prefer to stuck on each other, and this strange water arrangement is only on the interface between oil and water. So if you put it into some bottle, that's the area of this interface is just like the section of the bottle. But if you imagine that these molecules are like distributed individually in the liquid water, then you would get very, very huge area of this improbable water. So that's how like hydrophobic interactions, what is their driving force. It's all about entropy, it's all about this crazy water structure, and it's caused by the fact that this strange water structure where waters interact like with each other, but they do not interact in the direction of the molecule. This water arrangement is quite improbable.